So I'm going to talk in general a little bit about the activities in my group, but then in 10 minutes, of course, I'll try to focus one area, and that is lithium niobate integrated photonics, heterogeneous integration with silicon photonics. And it's a blessing to give this talk after Guifang's and Caitlin's, because it's in the same area, and it's nice that these three talks have this kind of the same general theme. So maybe I give a little bit of a bigger background why we do integrated photonics. In a nutshell, for the same reason we do integrated electronics. We want to have compactness, higher bandwidth, scalability, better reliability, and immunity to mechanical and other vibration. This is by no means a new area. At least you can trace it back to the late 60s, where in the Bell Labs, there's a seminal paper talking about integrated optics, which is essentially the grandfather of modern integrated photonics. So move forward, as Guifang introduced, the main application is essentially data communication, whether it is long haul communication or short haul communication in the context of data centers. So I'm showing in the left top the dream that we were showing about this around 2000. How you integrate lasers, photodetectors, and modulators, and other passive and active devices on the same chip, potentially having silicon electronics, CMOS circuitry on the same chip. On the right-hand side, I'm showing what really materialized by the mid-2005 on silicon photonics. Similar ideas in terms of devices, but what we do here is essentially data transmission. You have a bunch of lasers that you use as the light source. You have one bunch of modulators. You can think of them as on-off switches, and you use different wavelengths, wavelength division multiplexing, in order to transmit the data over a fiber channel, or maybe in the future shorter links. And then on the receiver, you demultiplex them and have photodetectors and photoreceivers and so on. Here is this company was called Luxtera, acquired by Cisco a couple of years ago. Here's indeed their pluggable format that they use for data centers, and I know by a few years ago they were selling, they're surpassing 1 million, sales of such products. So the best platform or vehicle to achieve this has been silicon photonics, as mentioned. Obviously, I'm not going to talk too much about this, but as Guifang was saying, you have a silicon layer, silicon and oxidized, silicon and silicon dioxide layer, buried layer, in order to have optical intercontrast and tiny submicron waveguides, dimensions of which are comparable to CMOS electronics, as opposed to, for example, silica LNA photonics, which is more similar to optical fibers, but rectangular shape. Again, my goal is, it's funny that I'm showing also the same thing that Guifang did, and thank you, Guifang, for complimenting me. My goal is not to talk about silicon photonics here, but rather its shortcomings and what will be the next generation. So light generation on silicon is not easily possible. Detection at telecom wavelength, as Guifang mentioned, is not easy because of the band gap. So people have been integrating germanium photodetectors and compound semiconductors, indium phosphide lasers for telecommunication wavelengths around 1.5 micron wavelength. So indeed, from the beginning, silicon photonics was heterogeneous in terms of material matrix that you use. So, but this is well known, and all the products do one way or other what I'm showing here. But what my team has been focusing more on in the last 10 years has other shortcomings of silicon photonics. Named here, lack of electro-optic effect in the traditional sense or strict sense of it, problems or lack of second and third order nonlinearities, and some other probably niche applications. For example, that buried oxide layer that we show is lost in the mid-infrared wavelength range. And as Guifang mentioned, polarization is another challenge in silicon photonics. So these are cartoonish, probably schematics. But in summary, say the materials that we've been working on over the last 10 years to address these issues. Here, the idea is to use silicon dioxide still as the bottom cladding layer for waveguides, but you replace the top material, silicon, with another material. And I'm going to focus more on lithium niobate. For mid-infrared applications, we've been working on a platform to eliminate this silicon dioxide layer completely, all the way going to all air-clad suspended membrane structures. Here are just some SEM images and references of some of the works we've done in this mid-infrared wavelength regime. But let me, and again, for the benefit of time, I'm going to skip this one, explaining it's a little bit more complicated. These are bifringent materials, meaning that the horizontal and vertical polarization components would behave differently. And indeed, this made it to the annual review of top works in optical photonics by the Optical Society in 2018. So let's, in a few minutes, I have focused more about lithium niobate. Lithium niobate is not a new material by any means. That's why I have the word rejuvenation in my title. It has several interesting properties. It's been used in surface acoustic waves and saw sensors for older, actually mobile technology, for MEMS applications and so on. But my focus is more on electro-optic and optical nonlinearities. These have been known again for decades. You can go in companies like Thorlab and buy an optical modulator or a wavelength converter for, which is essentially changing the wavelength of light or the color of light. So what's wrong with this? Well, these traditional lithium niobate photonics are based on waveguide platforms shown here, where the contrast of the core and cladding lesions of the waveguides is too small. So the waveguides are bulky. Here's the reflect contrast. Therefore, they are not suitable for modern integrated photonics, where you want to have several high level of integration, bending waveguides, and so on. If you could manage to make structures like this, for example, putting lithium niobate, tiny region similar to what we have with silicon, on oxidized silicon substrate, we're going to get back to business of many more improved devices in terms of at least electro and nonlinear optics. We made these wafers for the very first time in 2013 at Creole. I'm not going to go through the details of fabrication. Then we made devices on them. And indeed, what we've done in a sense is to move the key parameters, bending radius and effective area of waveguides, from around 10 to the power 4 micron bending radius to less than 100 micron, and in a way, essentially, it's about 2 orders of magnitude improvement in this area. This is an area, as I said, we started in 2013, and here is a more comprehensive list of papers we have in this field. So, and based on that work that I talk about, the wafers and waveguides, we also have a spin-off company, Parto Technology, that is the only US-based supplier of the wafers in the US. And there is a company in Asia, NanoLN, that markets the wafers too, and a lot of researchers have been purchasing the wafers from this vendor, and it's becoming essentially a blooming field. In a way, in the last review paper we wrote, we cited about 300 papers and in different areas of application of thin film lithium niobate. Essentially, what we are doing here is making a thin film of lithium niobate on oxidized silicon substrate. Here is summary of some of our work in this area. We made the first Mach Zehnder modulators, then the first high-speed ones operating up to 50 gigahertz. We made also micro ring modulators and wavelength converters. We have a few papers on this area, and here is a record high efficiency of second harmonic generation, meaning that you pump it at 1550 nanometer and you generate light at half that wavelength. These devices are so efficient that we see also cascaded nonlinearity, a second round of second harmonic generation, and some frequencies with second harmonic generation in order to emit visible light. We're also collaborating with a group at Northwestern University towards its applications in quantum optics. So, and there are predictions that we have on modeling of these devices that they can operate all the way to 340 gigahertz modulation bandwidth and beyond. So to give you an example of future directions, on the left, I talked a lot there was a lot of talk today about data communication and optical transceivers, but that's not the only application of integrated photonics in general and thin film lithium niobate in particular. On the left, I'm showing a DARPA program I had in collaboration with Peter Delphi at Creole and Ming-Woo Lee at UC Berkeley. Here you see we want to integrate indium phosphide lasers, chalcogen glass for third order nonlinearity and lithium niobate for second order nonlinearity towards, stabilized optical foam applications. Indeed, a very hot area these days. On the right hand side, I'm showing another paper that is indeed actually the seed of the seed fund I'm getting from IMEC and UCF. Here we use nonlinear wavelength conversion in order to make optical isolators. Optical isolators have been around in the bulk form for decades. Think of them as diodes in optics, but integrated forms have been elusive. Using these small lithium niobate devices and this novel concept that we have based on wavelength conversion and filtering would allow us to have integrated optical isolators. Indeed, one of the key missing components of the components that you need for integrated photonics. So I would end my talk here. Here is the pictures. I could not the names of all the students, the current and past, working in my group in this area, and I've also acknowledged the funding agencies and companies that have been supporting my research in the last several years. And thank you.